Now we will discuss another important equation is or theorem. Bernoulli, this is called Bernoulli's equation. That means the energy per unit volume before equals to energy per unit volume after. For a pipeline, there will be velocity B1 and for pressure P1 and velocity P2 for pressure P2. So we can calculate the pressure energy plus kinetic energy per unit volume plus potential energy per unit volume will be constant for any fluid. So now we'll discuss about this theorem. This theorem, according to the name of Daniel Bernoulli. He's a great scientist and mathematician from a Bernoulli family. There are about 6 scientists from this family. We'll discuss about the application of Bernoulli's principle. This is the fluid moving in a tube. So pressure plus P and so here actually this is the Bernoulli equation, and this total volume will be constant. So if no change in height, then this will be constant. This is the actually kinetic energy, and this is the total pressure. So this for the no change in height, potential energy will be 0. So this is the constant for this case. Now faster speed, this in this case faster speed, and this is the slower speed for the bigger tube, and for the smaller tube pressure will be high. This is why faster speed, and this is slower speed of liquid. So more pressure here and there less pressure. So as the speed of a fluid increases, the pressure in the fluid decreases. We have to remember this. This is the mainly Bernoulli's principle. As the speed of a fluid increases, the pressure in the fluid decreases. So pressure is proportional to 1 by B. If the speed is increases, pressure will be decreases. So motion of fluid actually due to energy, and pressure in fluid also due to motion of fluid will be kinetic energy and pressure of fluid will be potential energy. So we have to remember these two concepts. Now kinetic energy plus potential energy must be constant. So for this principle, if incompressible fluid density rho change in pressure, okay. So if the diameter becomes the 1/4 part of diameter, then it will be. This is the actual application of Bernoulli's equation in aeroplane and Bernoulli and flight. This is the Bernoulli principles is what allows bird and planes to fly. This is very real life example. So the secret behind the flight is under the wings. So air or wind giving pressure. So the faster air, less pressure, wing goes up, and air hits bottom of wing, bounces down, wings goes up. So airfoil, this is the on top greater air speed and less air pressure. On bottom, less air speed, the more air pressure. Okay. So for this reason, airplane flies speedily, and drag, that means more pressure, and thrust give more thrust. So lift the aeroplane to the sky, and due to the and behind the gravity. So there are four parts. One, lifting the aeroplane against the gravity because due to the drag or pressure, and give the thrust. So net force on wing will be like this: air or wind giving, and wings faster, more pressure up, so less pressure down. This is the application. So half a rho b2 square minus b1 square. This is the rho of air will be 1.29 kg per meter cube. So spoiler airfoil reserved, and greater air speed, less pressure. So less air speed, more pressure. Actually applying this principle, that means Bernoulli's principle, every airplane and flies faster. Net force equals to downwards. We can give this example also. Spoiler provides better traction and avoids lift. Wind over a roof. This is the proof. So atmosphere pressure equals to pressure on roof plus half rho b square. That means kinetic energy. Okay, this is the fast air speed, slow air speed, low pressure. And car ball also acting by using this principle: higher air pressure, flight path, and ball rotation. So lower air pressure. This is the no spin, but this will be spin because air pressure acting and thrust also acting. So flow fast a golf ball and turbulent boundary layer. Golf ball dimples and winds over a mountain. Here 50 mile per hour speed and 25 mile per hour speed, but at the top 100 mile per hour because there is due to the more pressure. And shower curtain, this is also, if you give the shower on a curtain, পর্দার উপর যদি আমরা পানি দিই ঝর্ণা থেকে, তখন এটার অ্যাপ্লিকেশনটা আমরা দেখতে পাবো। In speed of car, atomizer, as air passes at top of tube, the pressure decreases, fluid is drawn up the tube. So this is the application of Bernoulli. So for energy conservation, Bernoulli equation also can be written. Recall Euler equation, dp by rho plus b dv and z dz equals to 0. Also recall the force are neglected. Flow is in b seat. If one integrates Euler equation along streamline become 2 points. Just using integration, we get the actually Bernoulli equation. Here p1 by rho equals to flow of work, b1 square by 2 is kinetic energy, zz1 is potential energy, and this is the initial or before energy, and this is the last energy or final energy, and this equals to actually constant. So Bernoulli equation, flow of work, it is work required to move fluid across the contour volume boundaries. This is the actually consider a fluid element of a cross section area A and pressure P acting on a contour surface. So due to the work done per unit time will be rho, will be P at del x by T, and P by rho equal to this. That means P by rho equals to flow of work per unit mass. Actually, this is the Bernoulli equation. Okay. Now we'll try to derive the Bernoulli's theorem. Now, according to the Bernoulli's theorem, the sum of the energies possessed by a flowing liquid at any point is constant, provided the flow is steady and non-turbulent. Consider the incompressible liquid like water in a pipeline. The motion of the liquid is streamlined. Let the pressure of the liquid at the cross-section A1, A2, B, P1 and P2. The area of the cross-section will be A1 equals to A1 and A2 will be A2. So the velocity flow of liquid A1 is B1 and A2 will be B2. In that case, with the work done per second on the liquid entering A1 first surface area, W will be P1 A1 B1. So for the first, this is the actually tube and liquid passing through it. So this is the first surface area A1 and second surface area A2. Here pressure P1 and velocity B1, and here pressure P2 and velocity B2. And this is the for calculating the potential energy, this height will be H1 and this height will be H2. So for the work done for the second by the liquid leaving A2 surface area, so work done will be P2 A2 B2. Network done on the liquid will be W equals to W1 minus W2. In that case, the sum. But A2 B2 equals to A1 B1. This is the continuity equation we have derived in our previous slide. So this, by using a continuity equation, W equals to what will be just P1 minus P2 A1 B1. This work done on the liquid contributes for the changes in kinetic energy and gravitational energy. So change in gravitational energy, what will be? E1 equals to rho z. A1 B1 P1 rho z H2 minus S1. Change in kinetic energy will be half m b square. This is actually mass per unit volume. So total work done will be E1 plus E2. In that case, this equals to this. So just putting the values, we get this equals to this. This is the before and this is the after. So actually this is the constant b square by 2. This is the kinetic energy. This is the potential energy. This is the pressure. So this equation represents the Bernoulli's equation. Dividing equation 2 by z, we get this constant. Here b square by 2 z represent the velocity of head, and h represent the gravitational head, and p by rho 0 represent the pressure head. Special case, in case of horizontal pipe, a is the constant, b square by 2 plus p by rho equals to constant. So p plus half rho b square equals to constant, where p is called the static pressure and half rho b square is called the dynamic pressure. And this is alternate proof for this Bernoulli's equation. Just volume of the element will be this, mass of the liquid will be this. So forward force will be PA and backward will be P plus dPA. In this case, the downward along the x-axis acting force will be rho A dxz sin theta. Sin theta equals to actually ds by dx from figure. Okay, from figure we can write. We can use this method also for finding the Bernoulli's equation. So just integrating, we get this. Now application of Bernoulli's. A pilot tube is fixed on the wing of an aeroplane to measure the speed of aeroplane. The tube contains liquid density 800 kg per meter cube, and the level of the two limbs is 0.5 meter. Density of air is given. Calculate the speed of aeroplane. So half rho b square equals to is dz. Just putting these values, we get the velocity of aeroplane. Now, a benturimeter. A benturimeter consists of a horizontal tube as shown in figure. It is different cross section at A and B. Okay, this is the actually benturimeter. Here is the pressure P1 in A part and pressure P2 is B part. This is the size, small size, and this is the bigger size. That means volume bigger and volume smaller. So according to the Bernoulli's theorem, we get the total energy before equals to total energy after. If velocity B2 is greater than B1, therefore pressure P1 will be greater than B1 because pressure and force acting on opposite. The pressure difference at A and B is indicated by the manometer limbs. Now another application of Bernoulli principle. A horizontal tube has different areas of cross section at 2 points P1, P2. The diameter at P1 is 0.04 meter and the diameter at P2 is this. So 2 manometer limbs are fixed at P and Q when a liquid of density 800 kilogram per meter cube flows through. The difference in the pressure between the manometer limbs is this. Now calculate the rate of flow of the liquid through the tube. Now we get, according to the Bernoulli principle, energy before equals to energy after. This is the pressure P1 and this is the kinetic energy. This is the potential energy. So total energy before equals to total energy after. Now here H1 equals to H2 given height is same. This is why you can calculate BT equals to this. Now P1 minus PT equals to just putting the values we get. Calculate the speed at which the velocity of head of a stream of water is equal to the 0.50 meter of hg. Velocity of head will be b square by 2 g meter water. This is the formula for velocity of head, and velocity of head can be written, b can be found, b equals to 11.54 meter per second. Now, another application of Bernoulli's equation. A railway engine is fitted with a tube whose one end is inside a reservoir of water in between the rails. The other is the tube 4 meter above the surface of the water in the reservoir. Calculate the speed of the which water rushes out the upper end if the engine is moving with the speed of 108 km per hour. This is the total energy before and this total energy after. It's just potential and kinetic energy. Pressure is absent here. So just alternating, B1 equals to this and H1 minus H2 equals to 4 meter. This is the given values. Similarly, this is another example for you. This left for you. This is also another example left for the reader. Same formula for the horizontal pipeline. This is another example of Bernoulli's principle or Bernoulli's equation. A benerometer has a pipe diameter of 0.2 meter through throat diameter 0.15 meter. The levels of water column in the two limbs differ by 0.1 meter. Calculate the amount of water discharged through the pipe in 1 hour. Density of water is 1000 kilogram per hour per meter cube. So rate flow, this is the formula. Rho equals to given. So P1 minus P2 is given. So just putting the values. Similar example left for you. This is another application of Bernoulli principles. This is the Torricelli's theorem. Actually, this is the another advanced part of the Bernoulli's principle. So according to the Bernoulli's theorem, potential kinetic energy plus potential energy plus pressure equals to constant. So this is part A, and this is the height H1 from the O point, and this is the another height H2. This is the B point. So as P is the same at the free surface at the so B square by 2 plus ZS equals to constant. At A, B equals to 0, A is equals to S1. At A point, A is equals to S point, and velocity will be 0 steady. This is why. So ZS1 equals to B square by 2, or B equals to twice Z rays. The horizontal range L equals to BT, S equals to BT, distance equals to velocity multiply time. So L equals to B time root over 2S2 by Z. Just putting the values, we get the required. Now differentiating, this is differentiating with respect to L, and here we get dl by dh1 with respect to h1. For maximum L, first derivative will be 0. So first derivative equals to what? This 4h minus 8h1 plus 0. Here h1 equals to half capital H. Therefore, for the range of the liquid to be maximum, the or phase must be at the half of the height of the liquid of the column. Another example, a tank of containing water has an office on one vertical side. If the center of the office will be or fly switch 4.9 meter below the surface level in the tank. Just we have to find out the velocity of discharge. Actually, kinetic energy equals to potential energy. In that case, B equals to this. Just putting the values. This is very easy example for you. So actually, we have discussed here in Bernoulli equation and its application. So this is the Bernoulli's equation. We have proved as a fluid, and this given in 1738, Swiss physicist and mathematician Daniel Bernoulli derived the expression. So consequence of energy of conservation and applied to an ideal fluid. In deriving Bernoulli's equation, we again assume that the fluid incompressible fluid density is constant. Okay, consider the flow of the non-uniform pipe at the time del t. This is actually pipe or tube, and here pressure given F1 and a little change in length del L1 and velocity B1 here, and the height H1. Here height will be H2. Okay, and pressure will be F2 for this surface. So the work done will be force F1 del L1. So F1 equals to rho 1 A1 del L1. So del B equals to A1 del L2. That means work done first for the first part will be P1 del B. Here del B is the volume of the lower blue region in the picture. It is similar to the manner the work done for the on the fluid of the upper portion. This is the upper portion. So W2 will be minus F2 because the minus negative indicate the for the opposite force. So W2 equals to minus P2 del B. So the volume is the same because by the equation of continuity, the volume of the liquid that passes through S1 at the del T time equals the volume of the passes through the S2 part in the same interval. So the work done at 2 is negative because the force of the fluid at the top and opposite is displacement. The work done on the force at the time del T will be W equals to just difference. Total work done. Now total kinetic energy half m B2 minus B1 whole square, and the potential energy will be mg. H means what? Distance, difference between the distance. So total work done will be kinetic energy plus potential energy. So substitute the expression for each of the term, just putting the values here. Now if we divide each term by del B and rho equals to del m by del B, this is the space density. Density definition we have discussed in our previous slide. So per unit mass per unit volume is called density. So P1 minus P2 equals to this one. Just del B taking common. Now rearranging this part, P1 plus rho ZH1 plus half rho B1 square equals to, that means total energy before equals to total energy after. And this is the Bernoulli equation of an expressed as P plus rho ZH plus half rho B square equals to constant. So Bernoulli equation states that the sum of the external pressure P, this is the P is the external pressure, and hydrodynamic pressure, that means kinetic energy per unit volume. Kinetic energy per unit volume, half rho B square. And hydrostatic pressure. Hydrostatic pressure means the potential energy per unit volume. Okay, H rho Z has the same value at all points along the streamline or along the pipe or along the any tube. This is the main statement. This is the main statement for the Bernoulli's equation or Bernoulli's principle. And this is the Daniel Bernoulli, who is the founder of this equation. So an important consequence of Bernoulli equation can be demonstrated by considering picture. This is the picture we are discussing. So this is the total energy before and total energy after. So applied to points 1 and 2 gives, actually this is the constant. Application of Bernoulli's principle. Bernoulli's equation can be seen in various places around us. Here are some examples of Bernoulli's equation. This is actually train. A person who stands near a railway feels like falling into it when suddenly a train moves with a high speed passes him. It is because the velocity of air in front of him decreases. According to Bernoulli's principle, the pressure of the moving air decreases as the speed of the air increases. Okay, the higher atmospheric pressure behind pushed him forward. So this is the real life example for us to understand what is the Bernoulli's equation or Bernoulli's principle. So this is the shape of wing, and this in this picture force air travel faster over the covered upper surface, and it does over the flatter lower surface. According to Bernoulli's equation, the pressure above the wing is lower faster moving air for the faster moving air, while the pressure below the wing is higher for the slower moving air. The wing is lifted upward due to the higher pressure on the bottom of the wing. This is the real life example of Bernoulli's equation. And this is the Torricelli's theorem we have discussed in our previous slide. And applying Bernoulli's equation, we can derive this one. So consequently, you can apply this Bernoulli's equation obtained on the assumption that for the pressure in both section at atmosphere, therefore the same P1, P2 equals to P naught. In addition, velocity of the open surface, the weight vessels in the assumed equal to 0. So in that case, with a view to everything, everything said have equation 1 can be written in the following way. Okay, and B is the velocity of the liquid flowing from the hole. Cancelling rho and introducing S equals to S1 minus S2, that means the height of the open surface of the liquid above the hole. We get B equals to S twice root over twice Gs. This formula is known as the Torricelli formula. Torricelli formula. So after the Italian physicist Evan Gaslista Torricelli gives this formula. This formula can be states that the velocity with which a liquid is discharged from a hole at a depth of S under an open surface coincides with the velocity which a body requires in falling from the height S. This is the actually height is from this point. This is the S2 height and S height. So total S1. So S equals to what? S2 minus S1. Here, well, here in the upper surface, velocity is 0, but here velocity equals to B. So this is another example. Pitot pipe. We can this example given by Henry Pitot in the 18th century. Flow of velocity and pressure in horizontal pipe can be measured using vertical pipes. So this is the actually vertical pipes. This is another pipe. So however, Bernoulli equation in horizontal pipe for the horizontal pipe, this horizontal pipe will be this. And B1, if B1 equals to 0 and B2 equals to B, we can also can be written B1 equals to this. So since the difference of in pressure P1 minus P2 equals to rho Gs del S, so solving in flow of velocity, we get this B equals to root over. So fluid flow in ventimeter. This also can be application of ventimeter. Just using the continuity equation, ventimeter is a device to measure the flow speed of incompressible fluid like water. The basic principle on which it works is that by reducing the cross-section area of the flow passes, the pressure difference is measured by using different U types tube manometer. This is the U types, okay? And here this is the actually pipe. This is the A1 portion, this is the A2 portion. This is the bigger diameter, this is the smaller diameter. Here velocity B1 and velocity here velocity 2. So this is the height S1 The speed V1 is the liquid flowing through the tube, the inlet area A1 to be measured from the equation of continuity will be this. So the speed of the at the throat becomes B2 equals to B1 A1 divided by B2. Since the difference in pressure P1 minus P2 equals to ρ1 Gas, so using Bernoulli equation for the horizontal pipe will be this. So before energy equals to after energy. So P1 minus P2 equals to this. Now substitute the expression for each of the terms will be ρ1 Gas equals to this, because using equation number 2 here. Okay, here we get. Now solving for the speed B1 equals to this. It follows that the volume flow rate is equal to QB equals to A1 B1. This equals to this. Where the coefficient is determined experimentally, it is called the Bernoulli coefficient. Now we can solve some open problem for you. This is homework for you. So Bernoulli principle, we get Daniel Bernoulli found that the faster fluid moves, the less pressure it exerts. So Bernoulli principle means the pressure exerted by a moving fluid is less than the pressure of the surrounding fluid. Things move from area of high pressure to low pressure. This is the actually main, this is the application, how airplane flies, we have discussed in briefly here. And this is the application of Bernoulli's principle. This is another application, spoiler on a car and upside down wing. Okay, we have discussed this example. How may spray atomizer works like perfume bottle. Perfume bottle also works with the principle of Bernoulli. So this is the low pressure and high density. So squeeze valve and which makes the fluid move in top part, which lower the pressure. Fluid is in the bottom and it moves from its higher pressure area to top low pressure areas. So this is the actually Bernoulli principle. This is the different for the different liquids. This is the viscosity of selected gases. This is the standard values, and this is the fluid honey will be viscosity like this, and viscosity at 25 degrees centigrade. And viscosity of atmospheric materials. This is the temperature on x-axis, and this viscosity on y-axis. This is the references we have discussed. So thanks to everybody for being with us. So actually we have discussed the chapter fluid dynamics connecting with viscosity, these topics, and we especially have discussed the